So we're going to continue to look at rational functions. We'll graph and analyze and compare rational functions. And then we're also going to add something new, and that is determining whether rational functions have an asymptote or a point of discontinuity for the non-permissive value. So graphs of rational functions have a variety of shapes and different features. Vertical asymptotes are one such feature. So we've seen those before. A vertical asymptote of the graph of a rational function corresponds to a non-permissible value in the equation of the function. But not all non-permissible values result in vertical asymptotes. Sometimes we will get a point of discontinuity. So what that is, it is a point described by an ordered pair at which the graph of the function is not continuous. It is like a hole in the graph where you physically have to stop your pen or pencil, pick it up, move it, and then start again after it. It's just one point that's not part of the function. So it occurs in a graph of a rational function when its function can be simplified by dividing the numerator and denominator by a common factor that involves or includes the variable. It results in a single point missing from the graph, which is represented using an open circle. Again, it is sometimes referred to as a hole in the graph. So these come when you factor the numerator and denominator, and one of the non-permissive values is eliminated because you can cancel a common factor on the top and the bottom. If that common factor includes the variable, that means you're taking out one of those non-permissive values. When that happens, that non-permissive value gives you a point of discontinuity. If after canceling you still have a factor on the bottom that contains a variable, that non-permissive value will still give you a vertical asymptote. But any factor that cancels, that contains a variable, that non-permissive value will be the point of discontinuity. So it asks us to sketch the graph of that function and analyze its behavior near its non-permissible values. So the function f at x can be simplified because the numerator can be factored. It doesn't change the fact, though, that the non-permissive value is tied to the original expression. The original expression has a denominator of x minus 3, so therefore x cannot equal 3. The only question now is whether that value of 3 gives us a vertical asymptote or a point of discontinuity. So if we factor the top, the factors there will be x minus 3 and x minus 2, excuse me. And so what happens is that now you have a factor of x minus 3 on both the top and bottom. They cancel, and so your simplified expression is f at x equals x minus 2. However, we have to keep the same restriction that was there from the start, which is that x cannot equal positive 3. And because that x minus 3 canceled, that means in this case you're going to have a point of discontinuity at the point where x does equal 3. And if you take your simplified expression, which is just f at x equals x minus 2, and you let x equal 3 there, you get a value of 1. But x can't equal 3, so therefore y can never equal 1, and that is your point of discontinuity. The point 3, 1 is your point of discontinuity. There is a hole in the graph there. The rest of the graph is defined by our simplified equation, which is x minus 2. That's a line that has a y-intercept of negative 2 and a slope of 1. So you rise 1, run 1, rise 1, run 1. The next rise 1, run 1 would take you to the point of discontinuity, which is not actually part of the graph, but we can rise 1 and run 1 after that, and those are all points on the graph. So this is what this graph will look like. Starting from the point of discontinuity, heading upwards to the right and downwards to the left. That's what that graph will look like. It should be one line just with that break in it. So something like that. It is, and we'll see that. Keep my numerator and denominator in brackets. So x squared minus 5x plus 6 in brackets, all divided by, in brackets, x minus 3. Zoom 6 to set our windows to their standard settings. It just draws the line. Now, in the normal graphing mode, it actually doesn't show the point of discontinuity. However, if we go into trace and we let x equal 3, notice there is no y value returned because it's not an actual point on the graph. If you choose zoom decimal, zoom 4, sometimes you'll see the point of discontinuity. It just depends on where it is, because zoom decimal, it decreases the windows to around plus and minus 4 point something, I think. Or 6.6 on the x, 4.1 on the y. Right? But in zoom decimal mode, it actually does show the point of discontinuity. Just not in the standard graphing mode. Okay? So as x gets closer and closer to the non-permissive value, the value of y will approach a value of 1, because it does say analyze its behavior near the non-permissible value. So that's what's happening. As x approaches 3, then y will approach a value of 1. But it'll never actually get there because it is a point of discontinuity. So that is analyzing what's happening as we get closer to the point of discontinuity. All right? So on the next page, we want to do the same thing for f at x. So right now we have a denominator of x minus 1, so 1 is a non-permissive value. But let's see if that x minus 1 stays there. When we factor the top, the factors will be x plus 3, x minus 1. So now the x minus 1s will cancel, and we're left with f at x equals x plus 3. But we have to keep the same restriction that the original equation had, and that is that x cannot equal 1. But because that x minus 1 factor canceled, once again, that means we have a point of discontinuity. At the value that x equals 1. And we can take the simplified expression, let x equal 1, 1 plus 3 equals 4, so our point of discontinuity is at the point 1 comma 4. That's where the hole in the graph will be. The rest of the graph is defined by the equation x plus 3. That has a y-intercept of plus 3 and again a slope of 1. So rise 1 and run 1. Now, we can't do that because that takes us to the point of discontinuity. So we'll have to skip that point and continue to rise 1 and run 1. Or you can rise negative 1 and run negative 1. Those all work. So that's what the graph will look like. If you were asked to state the domain and range of this, the domain of this would be all values of x such that x cannot equal 1, but all other real numbers are part of the domain. The range, all values of y such that y cannot equal 4. but all other values of y belong to the range. Okay? So now we're going to compare these two functions. The only difference is that the numerator has the opposite sign in between. All the other terms are the same. So let's graph f at x. Again, the top, we have a factor of x. Take it out, you get x minus 2. If we take out a common factor of negative 2 on the bottom, we also get x minus 2. And then the x minus 2's will cancel. So that'll leave us with negative x over 2 or negative 1/2 x, but with the same restriction. And that is that x cannot equal 2. Because that x minus 2 factor canceled, that means again that we'll have a point of discontinuity at the point where x equals 2. And if we let x equal 2 in our simplified expression, y is negative 1/2 times x. Negative 1/2 times 2 is negative 1. So 2, negative 1 is our point of discontinuity. The rest of the graph is defined by y equals negative 1/2 x. That's a line that has a y-intercept of 0 and a slope of negative 1/2. Rise negative 1 and run 2 takes us to the point of discontinuity. So we can continue to rise negative 1 and run 2, or we can rise positive 1 and run negative 2. All these points will lie on the line. The domain of this again will be all values of x except for positive 2, all real values except for positive 2. And the range will be all real values of y except for negative 1. So that's what we know about f at x. Now for g at x. If you take out a common factor of x on top, we'll have x plus 2. Common factor of negative 2 on the bottom leaves us with x minus 2. So in this case here, you cannot cancel the factors. X plus 2 and x minus 2 are not the same. Nothing you can do to make them the same. But what this tells us, though, is because the x minus 2 doesn't cancel, in this case, we will have a vertical asymptote. At x equals 2. Right, so in this case, we'll have a vertical asymptote at x equals 2. Okay, the degree of the top is more than the bottom, so we don't have a horizontal asymptote here. The x-intercepts of this graph will be where y equals 0. and a rational function equals 0 when the top equals 0. The factors of the top are x and x plus 2, which gives us zeros of 0 and negative 2. So 0 and negative 2 are the two x-intercepts of this graph. And the y-intercept will be the same as the x-intercept, right? Because the graph goes through x equals 0, that means y equals 0 there as well. Okay? So to graph this function, we're just going to use our calculator. So if we go to y equals, and we'll put the expression in there, x squared plus 2x in brackets divided by, in brackets, 4 minus 2x. We'll set our windows back to their standard settings, and that's what it looks like. So we're just using this to get a rough idea. We can definitely, once we have it in our calculator, use our trace mode and find a few more points. For example, when x equals 1, you see y is 1.5. So we've got the point 1 comma 1.5, so that's there. Okay. When x is negative 3, y equals 0.3. When x is negative 4, y is 0.6 repeating, 2/3. This gives us one arm of the graph. It'll look something like that. And then to get the other arm, that's where x is greater than 2. So if x equals positive 3, y equals negative 7.5, which is way down here somewhere. Let's let x equal positive 4, negative 6. So that's right there. Positive 5, negative 5.83, almost negative 6. If we let x equal positive 6, we get negative 6, positive 7, we get negative 6.3, so now it's going down again. Okay, so something like that. There's that graph. And the domain and range, if we get those, the domain is still all values of x except negative 2. And to find out what the range is, we'd have to use our graphing calculator and find out where the minimum point is for the part that I'm circling, as well as the maximum point for the part that I'm circling. We'd have to find those on our calculator, which we can do. So I'm going to go second function trace. I'm going to find the minimum, number 3, between a left boundary of negative 4 and a right boundary of, let's say, positive 1. I'll put my guess at 0. It's actually something different. It's where x is 0.8. And you can see the value of y is negative 0.17 2 if you round to 3 decimal places. Negative 0.172. So this arm of the graph has a minimum of negative 0.172, and then it goes upwards from there. So our range has 2 parts to it. The first one would be from negative 0.172 up to positive infinity. So the negative 0.172 would be included, the infinity can't be, as well as the second arm, it goes from negative infinity up to this maximum point here. Second function trace, we want to find number 4 now, that's the maximum between positive, let's say 2.5 and positive 5. And you can see the value of y there is negative 5.828, it looks like. Negative 5.828. So this is going from negative infinity to negative 5.828, which is included, so we'd have the square brackets on that. Now you probably wouldn't be asked to find the range for something like that, but the calculator can be used to get it. The only thing is that you're estimating because you have to round those values. Unless you happen to get actually integral or rational values from the calculator, you're getting values that need to be rounded. And sometimes that might happen. Yeah, okay. Have a good break. So we're going to do the same thing for this one. If we look at f of x, we can factor the top, common factor of x, factor the bottom, common factor of 2, so we don't get factors that cancel. But negative 3 is still a non-permissive value. It just means that in this case we're going to have a vertical asymptote at x equals negative 3. Our x-intercepts are where the top equals 0, which are at 0 and positive 3. Because 0 is an x-intercept, that will also be our y-intercept. So again, to see what this graph looks like, we can put it in our calculator. The numerator is x squared minus 3x divided by, in brackets, 2x plus 6. We can, once we have this, generate a few more points. For example, when x equals 1, y is negative 1/4. So 1 common negative 1/4. Whoops, that's in the wrong spot. Approximately right there. When x equals 2, it's negative 0.2. When x equals negative 1, it's 1. When x equals positive 4, it's 0.3, and so on. So this arm of the graph would look something like that. For the other arm, we can start choosing values of x less than negative 3. Negative 4 is negative 14. Negative 5 is negative 10. Negative 6 is negative 9. Negative 7 or negative 8.75. Negative 8. Negative 8.8 it looks like. Or approximately a little bit higher than negative 9. And if we do negative 9, y is negative 9. So this gives us what the graph looks like, something like that. Next year, we'll actually learn that in these cases where the degree of the top is 1 more than the bottom, we actually get a slant asymptote. There's actually a slant asymptote here. This is not part of the 30-1 curriculum, but it would look something like that. So we'll learn about that in calculus. Okay? So that is f at x. So for g at x, common factor of x on top gives us x plus 3. And on the bottom, there's a common factor of 2, which also gives us x plus 3. The x plus 3's cancel, so we're left with x over 2 or 1/2 x. But we have to keep the same restriction, and that is that x cannot equal negative 3. So because those factors cancel, that means we'll have a point of discontinuity. Where x equals negative 3, and we can take the simplified equation 1/2 x and let x equal negative 3, and we'll get negative 3 over 2. That is the y value at the point of discontinuity. The point negative 3 comma negative 3 over 2. So negative 3 comma negative 3 over 2 is the point of discontinuity. The rest of it is defined by 1/2 x. So that's a line that has a y-intercept of 0 and a slope of a half. So rise 1 and run 2. Rise 1 and run 2. We can also rise negative 1 and run negative 2. Rise negative 1 and run negative 2. That works as well. But all these points will line up to give us our line, and they will also meet up with that point of discontinuity. So that's what that graph looks like. So where it says explain any differences, like you might see in a question on the diploma exam where it asks you to explain something, so you need to do that, right? So if we're going to explain the differences here, we would say that f at x has a vertical asymptote at x equals negative 3, but g at x has a point of discontinuity. At x equals negative 3. Okay? So that's what's different about the two graphs. So in this case, we want to match the equation of each rational function with the most appropriate graph and give reasons for each choice. So if we look at a at x, That function, we can factor the common factor of x on top, which leaves us with x plus 2. On the bottom, that's the difference of squares. The factors are x plus 2, x minus 2. The x plus 2's will cancel, so therefore we have a point of discontinuity at x equals negative 2, but we'll also have a vertical asymptote, because when you cancel the x plus 2's, you're still left with an x minus 2 on the bottom. So we will also have a vertical asymptote at x equals positive 2, which is why graph 2 would be the correct graph. That is the one that has a point of discontinuity at x equals negative 2, as well a vertical asymptote at x equals positive 2. So this is graph 2. So we can mark that one off. We've already dealt with it. Now, b at x, there's a common factor of 2 on top, but there are no factors on the bottom. You can't factor a sum of squares. Also, there are no non-permissive values for that either, because no matter what x equals, if you square it, you're never going to get negative 1, which is what you would need to get 0 on the bottom. So there are no restrictions on the domain, which is graph 3. Graph 1 has restrictions. It has 2 vertical asymptotes, but graph 3 doesn't. So graph 3 has no restrictions on the domain. And that equation has no restrictions on the domain. You could also say that the x-intercept of this equation would be negative 2. Remember, a rational function equals 0 when the top equals 0. The top will equal 0 at negative 2. So we can also say, and an x-intercept at x equals negative 2, which is also graph number 3. And that's the only x-intercept because that's the only 0. You could also confirm the y-intercept. That's when x is 0. You're going to get 4 over 1, which is 4. That matches the graph as well. So lots of reasons why that second equation works for graph number 3. So that means c at x must match graph 1. So let's just confirm that. When you factor the denominator for c at x, you're going to get x plus 2, x minus 2. Neither of those factors cancel, which means you're going to have 2 vertical asymptotes. At x equals both positive and negative 2, which is what graph 1 has. Okay? And then doing the same thing for these questions. First one, we check k at x. You cannot factor the top. The bottom factors to x minus 2, x plus 1, which means that we would have vertical asymptotes. At positive 2 and negative 1. Which is graph 3. So we can cross that one off. We've already dealt with it. The second equation, L at x, has a numerator of x minus 1. The denominator is a difference of squares. So we can factor those, and we can divide top and bottom by a factor of x minus 1, which leaves us with 1 over x plus 1. But because the x minus 1 cancel, that means we'll have a point of discontinuity. At x equals positive 1. And because we still have a factor of x plus 1, that means we'll have a vertical asymptote at x equals negative 1. Point of discontinuity at positive 1, vertical asymptote at negative 1. That's graph number 1. And so the last equation, m at x, the top factors, to x minus 2, x minus 3. The bottom, if we take out a common factor of negative 1, will give us x minus 3 as well. The x minus 3's will cancel, which means you'll have a point of discontinuity at x equals positive 3. And when x equals positive 3, and you let x equal positive 3 in the original equation, or in the simplified, I should say, 3 take away 2 is 1, but divided by negative 1 gives you negative 1. There's the point of discontinuity, 3 comma negative 1, which matches graph 2. As well, when you simplify this equation, you'll get negative x plus 2, which means it's a line that has a y-intercept of plus 2 and a slope of negative 1. That also matches graph number 2. Okay? So you can do those questions for practice. I will put the solutions on Google Classroom so you can check your work. But you should definitely do those questions for practice. You have to get your textbook.